Welcome to this lecture, and actually the topic that you can see, the fundamental concepts of design and the static load. I'm going to cover this particular topic in 3 consecutive lectures. In the first lecture, I am going to basically cover the different kinds of load that comes in the machine components, and because of those loads, what are the stresses that is developed within the material and how to calculate those stresses. Okay, so this fundamental concept of design under static load, having basically it is divided into 3 major subtopics, I would say. First thing is that when some load is coming on a machine component, first thing is that we have to identify, or we have to find out that what are the stresses coming because of that load. So that is the first part, and in this lecture our main objective is to find out that. In the next lecture we will see the concept of principal stresses, and in the final lecture we will see how, with the help of failure theories, we take a decision whether our design is safe or how to make a safe design. Anyhow, the objective of the whole the topic that has been shown, having these points, basically the types of load and stress calculation for given loads, and the first 2 subtopic that you can see we are going to cover in this lecture. In the next lecture we'll see the stress element and principal stresses and Mohr circle and strength of materials, and in the final lecture we'll see theories of failure and some of the practical worked out examples by which we will take certain decision about the design. So this is the topic of this particular lecture, where we are going to discuss on types of different kinds of loads acting on a component and stresses induced because of those loads. So here you can see the tension in the first picture. Suppose this is a component, and tension is coming. Here you can see tension is a kind of force by which this particular component will be elongated. Okay, there will be a tendency of elongation because of this kind of force. So this is what is called tension. In case of compression, just the reverse. Because of this kind of axial force, what happens? The component will try to contract. Okay, so tension and compression, these are kind of axial forces, and because of which you can see that either material will have a tendency to elongate or compress. Now coming to this particular kind of a load, which is called the shear. Here you can see that with respect to one end, if you tangentially give a force on the other end, then it will have a tendency to change its shape, and this particular kind of forces are called the shear forces. And shear forces is a definite kind of load that is coming on many machine components. And then you can see torsion. Torsional load is basically one end with respect to one end, if other end having a twisting moment with respect to its body axis, that is what is called the torsion. Okay, so this torsional load is also very common in different machine components. And finally you can see the bending action. Here you can see with respect to, if you consider this as the axis, and you can see the transverse load is acting, and that is why there is a chance of bending of that particular beam. Okay, so we'll see these are the primary loads that is coming on the machine components. But remember, in practical situation, because of the complex loading, it is very much possible that combination of them are also present. It is not that only compression or only torsion or only bending will be there. It is possible that combination of them are also present. Now one by one we will look each kind of load, and because of that what kind of stresses will come in the member. So first we will take this kind of load, which is called uniform axial load. This uniform axial load, we have seen in the last picture that it can be either tensile or either compressive. Here you can see either tensile or compressive, these two are under the category of uniform axial load. Here you can see some of the practical examples. Here you can see this is a bridge truss. Here you can see these particular structures are called the truss structures, and here this is the roof truss. So in bridge, in roofs, you can find this kind of structures, and these members, these truss members are having you can see that this kind of axial loads. That means they are either in tension or in compression. Okay, so you can see this particular green member that you can see, and this member is a component of the structure. This is what is a truss member, and this is under either tension or under compression. Okay, so this is what is you can see. Now if you want to see what kind of stress will be developed at a point, here you can see one particular component is taken within the member, and you see the because of these forces, because of this kind of tensile forces, here you can see the normal stress is developing. The normal stress is what? The stress that is acting normal to the surface. The uniform axial load, because of the uniform axial load, the nature of the normal stress is such that throughout the cross section, that means throughout this area, throughout this cross section, the magnitude of this normal stress is same, and that is uniform. Okay, so uniform normal stress, and that is tensile in nature, that will be developed because of this tensile load. Similarly, if the load is compressive, then uniform compressive stress will be developed throughout the cross section. Okay, now if you want to measure the magnitude of that tensile stress or the compressive stress, then the formula is very simple. The stress, normal stress that is developed, will be equal to the load that is acting P. If that is P, then that P divided by the whole cross sectional area A. Okay, so because this sigma is uniform throughout the cross section, so simply P by A is the calculation of this kind of normal stresses. Okay, so this is what is the how stress due to axial load is calculated. Now coming to uniform shear load. Now uniform shear load is a situation. Here you can see that you have seen this kind of rivets. This kind of rivet joints are very component in different structural and machine members, and you can see these are suppose two plates. This two blue plates are there, and consider this yellow one is a rivet. Okay, now if you these rivets actually join these two plates against this kind of forces. Suppose two forces are acting on these plates, then definitely the stress will come on the rivet member. So what kind of stress will come? The nature of stress will be the shear stress on the rivet. Okay, so here you can see, if we draw the free body diagram of the rivet, you will find that this rivet will experience this kind of forces. And now if you just cut, and either if you take the top portion and draw the free body diagram, you will find that this force is there, and the bottom end throughout the cross section you will get a resistance force, and this force is basically what is the shear force P. So if the shear force is P, and if the cross sectional area of that rivet is A, that cross sectional area of the rivet is calculated. If the diameter of the rivet is a D, then pi by 4 D square is the area of the cross section of the rivet. So you can find out that easily. So that force P, that the shear force P divided by that cross sectional area of the rivet will give you the measurement of the shear stress. Now if you take a point on it, you will find that the shear stress will act in this way. Now here you can see that how shear stress is calculated, the shear force divided by the cross sectional area. So what is the cross sectional area of the bolt here? You can see that is pi by 4 D square. So either it is a bolt or a rivet, this kind of shear is very common, and yeah, that is why in case of bolts or the rivets, they are basically designed considering the shear. Okay, and the shear stress developed, remember, P divided by the cross sectional area of the bolt. Now coming to torsional load. Now torsional load is commonly seen in different shafts. Okay, so here you can see that this is a line shaft. Here you can see this one is a line shaft, and there are different pulleys are attached with the line shaft. So the power from the line shaft is coming to different machine through this pulley. Here the picture is much more clear. Here you can see this is the line shaft, and at different machines the power is taken through the pulley from that line shaft. Maybe the line shaft is running through some motor, with the help of some motor, and from that line shaft the power is taken to different machine with the help of pulleys that you can see. So here is a simpler picture of what is a line shaft. Okay, or you can see here it is the pump shaft, where the motor is driving the shaft, and through the shaft power is transmitted from the motor to the pump impeller. Similarly, here you can see the crankshaft. In a crankshaft, you know, the engine power is transmitted. Okay, so this is what is the crankshaft. So all these are kind of a rotating device where the load is basically the torsional load. Or you can see the camshaft. You know that camshaft actually controls the opening and closing of the inlet valves and the exhaust valves in the engine cylinders. Okay, so in camshaft also, or you can see the drive shaft. Through the drive shaft, you know, the engine power is going to the driving wheels in the axles. So this is the shaft. So all these shafts that you have seen are basically under kind of torsional load. Okay, so if a member is under torsional load, then what kind of stresses are developed within the member? Remember, if it is under pure torsion, then the stress that will be developed is a pure shear stress developed. Okay, so if you take one element and if you see that the shear stress will be developed, remember shear stress will be developed if it is under pure torsion. But remember, here the shafts that you can see in the different members, it is not a pure torsion that is acting. Along with the torsion, you can see because of the weight of the different members, or in the line shaft, the loads are coming at different points. Because of that, there will be a bending of the shaft also there. So that is why basically these shafts are under both bending and torsion. It is not a pure torsion situation, but if you consider the particular shaft is under pure torsion, then it will be a pure shear stress. But if it is having both bending and torsion, then the stress because of bending and stress because of torsion, both you have to consider in that particular element. So here you can see the shear stress developed due to pure torsion. Okay, so how can I find out that? This is the formula to find out the shear stress developed because of pure torsion. If the amount of twisting moment present is T, okay, if this is the torque, and if R is any radial position, say from the center or from the axis of that particular shaft, that is R, and if J is the polar moment of inertia of the cross-sectional area where you want to find out the shear, then tau shear stress will be T into R by J. So you can see that this shear stress is not same throughout the cross section. Okay, so but this shear stress is continuously varying from the axial location to the outer periphery. At the outer periphery, definitely the shear stress will be maximum because there R is maximum, and at the axial location the shear stress will be 0 because R will be 0. So shear stress is actually increasing as you move from the axial location to the circumference. Okay, so this is how the shear stress is varying within a cross section. Now if you want to find out where the shear stress is maximum, in that case definitely you have to consider an element which is at the outer surface, and you can see that tau max will be equal to the torsional load acting at that section multiplied by its radius of the shaft, that is d by 2, if d is the outer diameter, d by 2, divided by polar moment of inertia, which is calculated as pi by 32 d to the power 4. Okay, so in this way we can calculate under pure torsion the maximum shear stress which is acting at the outer surface. Now consider another kind of loading which is or the bending load and bending load in beams, and you can see the different structures where these are called beams. Here you can see an aeroplane wing where the loads are coming because of these engines, turbo engines are there, they having load, so it is like a cantilever beam and these are the different loads. Okay, here you can see another cantilever beam in a structure, you can understand. Here you can see the signals, the traffic signals are actually hang from a cantilever rod. So you can see all these are beams where some kind of bending loads are acting. Because of this kind of transverse load, there is a chance of bending of that member. Okay, so because of the bending load, we'll see that what kind of stresses are coming in this particular members. So because of bending, normal stress and shear stress both are developed. Okay, the normal stress that is developed because of bending is normally called bending stress. So bending stress is what? Because of bending, the normal stress that is developed, and that is calculated by the formula m into y by I, where what is m? This m is the point where you want to know the bending stress at that location, what is the bending moment, that you have to calculate first. So from the load diagram, first you have to calculate the bending moment at that location where you want to know that bending stress. Then you have to multiply it by y, where y is the position of that particular fiber or point from the neutral axis. Neutral axis is the axis where there is no deformation of the fiber. That means because of bending, you know, if you see the top fiber, that will be contracted and the bottom fiber that will extend, but you will always get a fiber in between, some intermediate fiber where there will be no elongation or contraction. So that particular layer of the fiber is the neutral plane. Okay, so from the neutral plane, the distance of that point is what is y, and I is the second area moment or area moment of inertia of that particular section with respect to neutral axis. Okay, so by this formula we can find out what is the bending stress at that particular location. And here you can see that bending stress is definitely a function of y. Y means as you move away from the neutral axis, then the bending stress will gradually increase, and definitely at the highest value of y, that means either at the top or at the bottom, the y will be either a maximum. Okay, so bending stress will be maximum or minimum at the top or bottom fiber. Okay, so depending upon whether it is tensile or compressive, that decision definitely you have to take. In this particular example, you can see at the top fiber it will be compressive, and at the bottom fiber it will be tensile in nature, because if you see this will bend like this, that means the top fiber will be contracted and the bottom fiber will be elongated. So bottom fiber it will be under tension and the top fiber that will be under compression, and the maximum value you can calculate using this formula, the stress. Now because of bending, not only normal stress developed but also shear stress is developed. Now shear stresses because of bending can be calculated by the formula tau, which is shear stress, is equal to V. V is the shear force that is acting at that section, into Q. Q is the first area moment of the area above that area up to the extreme surface, that means either top or the bottom surface. That means suppose if you want to find out that Q for this particular point, then from that point if you consider the top surface of that particular section, then first area moment of that area is what is Q, and I is the second area moment of the area, and B is the width of that particular section, the width of the section at that distance where you want to find out the shear stress. And definitely you can see that shear stress is not same again throughout the cross section. Rather shear stress is 0 at the top or the bottom fiber. Okay, but the shear stress is maximum at the neutral axis. Okay, at the neutral axis, because from the neutral axis you will get a much larger area. Okay, so for that you will get a larger Q, and that is why the shear stress will be maximum at the neutral axis, because first this Q is basically first area moment with respect to neutral axis. Okay, so shear stress distribution in case of bending, you will find that at the it will be 0 at the outer surface, or at the that means at the top surface or at the bottom surface, and the shear stress is maximum at the neutral axis. Okay, on the other hand, you have to remember that shear stress because of torsion was maximum at the outer surface and 0 at the axial location, but for the bending the shear stress is just opposite. That means it is maximum at the axial neutral axis and it is maximum at the outer surfaces. So that you have to remember. Now if you take this element, and that element has been shown and how the stresses are acting, you see for this element definitely it is above the neutral axis, so all the fibers will be in compression, so you can see the normal stress will be compressive in nature, and they definitely shear stress will be there, and the shear stress directions has been shown, and the magnitude of tau and magnitude of sigma will be according to these two formulas. Now coming to another kind of loading, that is because of the internal pressure within this kind of pressure vessels. Here you can see the propane tank or liquid nitrogen storage tank or ammonia tank or LPG cylinder or a boiler shell. Everywhere some internal to these pressure vessels certain pressurized gases are there, right? So because of those pressurized gases or liquid, what happens, it produces pressure, and that definitely because of that stress will come in the material, the thin material of the shell, the pressure stress will come. Now what kind of stresses will come because of these pressure vessels, internal pressure? Okay, so that we'll see. Now here you can see the stresses will be tensile in nature. Here you can see because of the internal pressure in a cylindrical vessel, suppose the biaxial stresses are acting like this at the outer surface. You can see that sigma L, which indicates the longitudinal stress, and sigma theta, which is circumferential stress, that is acting. So you can see two normal stresses in two different axes that will act. Okay, and there will be no shear will act within a pressure vessel unless otherwise some torsional load is applied. If only internal pressure is there, you can see two normal stresses, and those are tensile in nature, will be developed. Now their magnitudes can be calculated from this formula. You have to remember, for the longitudinal stress it is by PD by 4 into T, where T is the thickness of that thin walled pressure vessel and D is the diameter, okay, diameter of the pressure vessel. P is the internal pressure, and you can see that as the internal pressure is more, definitely the stress will be more, and if the thickness is small, then stress will be more. Okay, if the diameter is more, stress will be more. So these are the certain things that you have to remember. Okay, now you see sigma theta is PD by 2T. Okay, now if you just compare the sigma L and sigma theta, and from the expression it is quite clear that sigma theta is larger than sigma L, rather twice of sigma L. Okay, so this circumferential stress is also called the hoop stress. Okay, sigma theta, the circumferential stress is also called hoop stress. So hoop stress is larger in magnitude with respect to longitudinal stress, and its value is PD by 2T. So this is the main observation that you have to remember. For a spherical pressure vessel, you can see that since the radius of curvature is same in all directions, that is why the stress definitely again will be normal, but that will be of the same magnitude, and it will be of the value PD by 4 into T. Okay, and you can see this is again normal stress and this tensile in nature. So in this way, in case of thin wall pressure vessels, we can also find out what kind of stresses are coming in the material. Now coming to a rather more realistic situation, where combined loading. Here you can see one example. Let us consider that this is a signboard, and because of some wind load, definitely some stress will come on this particular pole. Okay, so let us try to find out what kind of stresses will be developed at this particular cross section, which is say about 2 meters from the ground. And in this cross section, if we see 4 points we have actually marked at a different location of that cross section, A, B, C and B. So this is basically this particular location. I hope you have understood that what we want to find out. We want to find out the stresses acting at these different points A, B, C and D. What kind of load is coming? The load is, you can see that wind load is coming from negative x direction, that you can see in this direction the force is coming on this particular signboard. Now you first tell me that because of this force, what kind of loading is basically coming. So definitely one kind of loading is the torsional loading, because of this load, definitely that will try to twist this particular member with respect to z-axis. So a twisting moment will come, and because of torsion, you know that shear stress developed. Okay, so first you just consider that torsional moment and see. Here we have shown that at different points A, B, C and D, these are the stress elements, suppose. And because of torsion, what kind of stresses will come? We know because of torsion, shear stresses come. So what will be the direction of the shear stresses at different points? Definitely this will try to rotate with respect to z-axis because of this load, right? So definitely at point C it will be in this direction, at point B it will be in this direction, at point A it will be in this direction, and at point D it will be in this direction. Let us take marker. And so since with respect because of this load, definitely it will try to rotate with respect to z-axis of that pole. So the shear stress that will come on C in this direction, on B in this direction, on A in this direction, and definitely on D in this direction. Okay, this kind of torsional moment will come. And because of torsion, what stress is coming? You know, because of torsion, shear stress is coming, right? Now that what will be that shear stress because of torsion? Now at point B and at point D, you can see that if you apply this kind of a torsional load on the element at point B and D, these are the point where what will be the, so first consider that point B. So what will be the direction of the torsion? You can see the direction of torsion will be this one. Okay, that you can see direction of torsion will be this one. What will be at D? Tell me. At D the torsion direction will be this one. Clear? And if at B it is this one, then definitely the opposite will act at the bottom in the opposite direction, and to make it equilibrium, definitely in these two opposite surfaces that shear will act so that it will be in equilibrium. That is why this shear is also present. Okay, you have understood, I think. But that means at this point this is there, so definitely at the bottom it will be in the opposite direction. So this will try to rotate the whole thing in this direction, that means in this direction, and definitely for a rotational equilibrium there will be just opposite to this direction, this one and this one, this particular couple will be created so that it will be in equilibrium. So ultimately the thing will be in rotational equilibrium. So that is why you can see this face and this face, the shear stress will be in this direction. Similarly in the D, that you can see in this direction, so it will be at the bottom surface in this direction, and to counterbalance this particular rotation, definitely in this direction and in this direction the shear stress will also develop. Okay, now coming to what about A and C, you can see at A it will be in this direction and C it will be in this direction, that you can see. At C it will be in this direction, at A it will be in this direction. At A it will be in this direction, so definitely in the opposite it will be in this direction, and to counterbalance this one, definitely opposite shear stresses has to be there. That is why you can see in this phase shear stress in this direction. Similarly for C also, since the shear is in this direction, so definitely in the opposite it will be in direction. This will try to rotate in the anti-clockwise, so to make a clockwise movement in these two phases, this kind of shear will be there to make it. So by this red color we have seen what are the different stresses, shear stresses that will be developed because of torsion. Okay, now we see what is the effect of bending on that particular cross section. Now bending, you first tell me that what kind of bending will be developed. Definitely you can see that it will create a bending moment with respect to y-axis. That is sure, because if you apply a force in this direction, definitely that will try to rotate, bend in this direction. Okay, so you just consider this is the pole, suppose this end is fixed, and as if you are giving a load like this, so definitely it will try to bend in this way. So bending will come on this section. Now if you just consider that bending effect, we know because of bending what happens. Because of bending, two kinds of stresses are possible. One is normal stress, another one is shear stress. Let us first see what is the normal stress because of bending, and that has been shown by the green. Now if you remember the expression of the normal stress because of bending, that sigma is equal to my by I, right? Now if you consider the bending with respect to y-axis, you just think that means it is like a bending with respect to BD axis. Okay, so with respect to BD, it is, if it is trying to bend, then you tell me at point A it will be what, and at point C it will be what? It will be tensile or compressive, because it is going to bend like this. So when it will be going to bend like this, then definitely this A point will be the outer face and this will be the inner one. So outer one definitely will be under tension and the inner one will be under compression. So definitely the normal stress developed at point A will be what? Under tension, and at the C the normal stress developed will be under compression. So you see that at the C point you will find this kind of compressive stresses, and at the A point you will find the normal stress that will be tensile in nature. Okay, so at A and C you have understood. Now what about B and D? Since the bending is taking place with respect to BD, so BD is as if the neutral axis. So at B and D there will be no bending stress, because at B and D y is 0, because with respect to neutral axis, this y is basically the distance from the neutral axis. Both B and D are at the neutral axis. Now coming to shear stress because of bending. Now shear stress, you know what, that shear stress is maximum at the neutral axis. Okay, so at B and D you will get the maximum shear stress because of bending, whereas A and C are at the outer surfaces where shear stress because of bending will be 0, and that is why you cannot see any shear because of bending at A and C. But at B and D definitely you will get that shear stress, and that you can see from here. So you can see at point P you will definitely get this kind of a shear. That is quite clear because it is trying to move in that direction. Then definitely shear will be in that direction. That is why you see both B and D, the shear will be in this direction, and definitely to counterbalance that, the shear opposite phases will be in this direction. So in this way different kinds of combined stresses will come in the element, and our main job from the loading is to identify these elements. This is what is the most important thing, to identify these elements, stress elements. These are called the stress element, where we'll show the different stresses, normal and shear stresses on that element at different phases. Once we can identify the stress element from the loading, then we'll go to the next step. Okay, so in this lecture, what we have seen, we have studied the different kinds of loading, different types of loading, and this type of loadings create stress in the material, and how to calculate those stresses, that we have seen. And we have also mentioned that these stresses may be developed because of combined loading. In that case, we have to separately consider each kind of load, and because of that, what kind of stresses are coming, and depending upon their directions, you have to add those stresses. And finally, what we get the stress element, and in the stress element we will be able to identify the normal and the shear stresses. And now, based on the normal and the shear stresses, we have to find out that where the maximum normal or the shear will come, and that will be the topic of our next lecture in the principal stress. Okay, so thank you.